Hey everybody, welcome back. Moving on with our electrochemistry unit. We're going to talk about section 2, 21.2. 21.2 is all about voltaic cells. How they work, different ways we represent them, different parts to them. Good thing to do. It's kind of strange that our book actually mentions them at the end of the previous section. So take a quick look. There's only about, I don't know, like a couple paragraphs. It's called An Overview of Electrochemical Cells. Just kind of some good background information before really diving into this section right here. It's on page 924, and like I said, it's just a really short little blurb with some diagrams, some good ideas, some good terminology, lots of boldface words all in that section. So take a look at it. We'll be going into more details about every single one of those terms throughout the rest of the chapter. But if you want a good kind of summary, then look no further than that little section right at the end. It's the end of section 21.1. I didn't actually cover it in the previous video, but give it a read. Okay, if we do start with 21.2, voltaic cells. Voltaic cells are actually very, very neat. If we take, say, zinc metal, and we place zinc metal in a copper nitrate solution. So zinc metal goes into a solution of copper nitrate. Real quick again, nitrate, what's it doing? Not much, right? The nitrates don't do anything, not reacting, it's a spectator. You'll notice that a lot throughout this chapter. Recognize your spectators. We only focus on the ions and the metals that are actually reacting. If you place zinc metal into copper nitrate solution, what you find is that a spontaneous reaction occurs. And there's that word spontaneous again. We'll be using that one throughout this chapter as well. If you were to place those two things together, our reaction would be zinc solid. Our net ionic reaction would be zinc solid, reacts with our copper ions, and we would make copper solid and zinc ions. A lot of the reaction writing is going to be very familiar to our activity series lab that we did a long time ago, back in first semester. But a lot of the information and the work we did then actually carries over to what we're learning now. So here's our net ionic. If we compared the activity series, we would see since zinc is being turned into an ion, zinc is actually, we see zinc is more reactive than copper is. Zinc is being oxidized into zinc 2 positive ions, and copper is being reduced. So here's our overall redox reactions. So we see here, electrons are transferred. Oops. Electrons are transferred, and a redox reaction occurs. But what's sad about this is if we do this reaction, say in a beaker, right? Not too hard. Fill a beaker up with copper nitrate solution, drop some pieces of zinc, boom, the reaction takes place. No problem. You guys have actually done this reaction as part of your lab a few times. Very, very easy to do. But the neat part is, hey, if those electrons are transferring between the zinc and the copper, let's find a way we can actually collect them. And that's exactly what a voltaic cell is used to do, that we'll take a look at here. Okay. So now we say to produce an electric current, we need to separate the zinc and the copper. We're going to separate each half reaction into its own cell. And we're going to connect those cells with wires. Oops, wires. Here we have a diagram of a voltaic or galvanic cell. Voltaic or galvanic. They mean the same thing. Cell. So right now we have, I know it seems like a really complicated picture with lots of details. Yes, this is something you do want to be able to know how to draw. You would want to, let's just point out the major features here. You would draw a beaker, two beakers, one here, okay. Notice here we have a piece of metal. That piece of metal is our zinc, okay. That's our zinc metal, our zinc solid. And it's dipped into a solution of actually zinc nitrate. Okay, so you have the zinc metal in a solution of zinc ions. Again, the nitrate's not doing anything. Now in our other beaker, we have here copper metal. Here's our copper solid. Okay, so you have a copper solid, a copper electrode, and this is a zinc electrode, this is a copper electrode, and it's dipped into a solution of copper ions. See, here's our copper 2 positive. It's copper nitrate. Again, nitrate's not doing anything. The copper, though, ions are. Those are our two beakers. These are our two cells. Now, these two cells by themselves are useless, so we need to connect them. Here are the wires that we connect. Okay, you can connect a wire straight from the zinc electrode to the copper electrode, but for the most part, we connect it to what we call a voltmeter to actually measure voltage. Now, if you're familiar with circuits at all, you'll know that circuits always need to be connected in a type of loop, have to complete the circuit. So that's what this apparatus is here. This is what's called a salt bridge. So a salt bridge connects one beaker to the other, one solution to the other. And in that bridge, it's called salt for a reason, it has a salt. In this case, it's literally table salt, NaCl. What's important about the salt bridge, very important about the salt bridge, is the chemical that's in your salt bridge cannot react with anything. Okay, we'll talk about here now how this all works. If you can follow along, maybe look at the diagram that's in our book too. It's got a really good one. You can take a closer look at it. Let's see. So in here, zinc, if you'll notice, if you look back at the reaction up above, zinc was being oxidized. So here's our half reaction, our oxidation half reaction. Zinc solid turns into zinc 2 plus 2 electrons. Okay. Then over here, with our copper electrode, we have the copper reduction. So you have copper 2 positive plus 2 electron goes to copper solid. That's our reduction. Okay. So you have oxidation here on the left, reduction on the right. In fact, that's usually how galvanic cells are drawn. They're drawn with the oxidation on the left and the reduction on the right. That's not anything that has to be guaranteed, but it's typically done that way. So what's actually occurring here is a number of different things. According to our reaction, zinc solid, right, zinc solid is turning into zinc ions. So what happens is the zinc solid is actually losing 2 electrons. 2 electrons come off, and those electrons travel up the wire. And the zinc solid turns into zinc ions. Notice the arrow here. Zinc solid turns into zinc dissolved ions, zinc 2 positive. And those electrons travel through here, they come all the way over here, and this is where copper, the electrons travel all the way down, and this is where copper ions gain them. Notice our reduction, copper ions plus 2 electrons. The dissolved copper that's floating around in our solution actually gets attracted to those extra electrons, and they go and gather on the copper metal. So here in these images, these atomic pictures, you'll see zinc is slowly losing, the zinc solid is slowly becoming the ions. It's going off into the solution. And here, the copper ions are actually attracted to the metal, and they're turning into copper metal. Which one did I say? Anyway, copper. Copper ions are being attracted, and they're turning into the copper metal, copper solid, and they're gathering. This is a kind of a real picture of what these two electrodes would look like. Notice the zinc has gotten significantly smaller because this is zinc solid turning into zinc ions. And notice the copper has gotten significantly bigger. And this is copper ions gathering and turning into copper metal. Now the salt bridge, here, if the salt bridge didn't exist, if you just have electrons flowing through the wire and going from one side to the other, you just have a huge buildup of charge. Charges would build up over here a ton, and charges would build up over here a ton, opposite charges. Okay? You're dissolving lots of zinc, you have a whole bunch of positive charge building up in here, and I've got electrons flowing through this wire, I've got negative charge building up all over here. So the cell would actually cease to function. So the salt bridge allows the charges to stay balanced. So what happens is the salt is composed of a soluble solid, NaCl. The Cl minus, notice an arrow shows it going this way. As the positive charge builds up here, negative chloride ions come down here to balance out that charge. Again, the salt doesn't react with anything. Cl minus is just spectating, but it's keeping the charge balanced. Likewise, sodium positive ions flow this way to balance out the buildup of negative charge here. As long as charges don't build up, this flow of electrons and charges will continue to run. Once all the metal has reacted, either you run out of copper ions here or you run out of solid zinc here, that's when the reaction would then stop. But this reaction will continue to flow until that point occurs. Okay, at this point, if you do want to take a second and maybe draw out a simple version of this diagram, draw out the two beakers, draw and label your copper and zinc electrodes, draw your salt bridge, connect it up with some wires, label a few things if you want to do that. Now would be a good time to maybe pause the video and do it. Maybe you already did. Fantastic. But yeah, definitely take a second, get that drawn out. Okay, I'll assume you're ready to go. Let's see. Two key important terms to point out here. The zinc side here, this is called the anode. Okay, anode is where oxidation occurs. Anode, oxidation, oxidation, anode. And the opposite over here is our cathode. Okay, the cathode is where reduction occurs. Okay, we call the area of the cell where reduction happens, we call that the cathode. I know that this negative sign and positive sign are labeled here. That's actually not information you need to know. AP exam and myself will not expect you to label positive and negative charges anywhere. What's the positive end here and the negative end here? So you can ignore that if you want to. But what is important are these terms, cathode and anode. Anode is oxidation, cathode is reduction. Simple trick to remember, reduction and cathode, red cat. Red cat. Cat is red. Red cat, red reduction. Reduction cathode. I guess it kind of works over here too, although I don't like this one. Anox. I don't know. No one really talks about oxes. Whatever. Anox. I don't know, you can come up with something. Anox. That works. I like the red cat. As long as you know one of them, then by default you should know the other one. And you're good. Last thing to mention about this diagram, super important, can't stress enough, this whole diagram is a major part to electrochemistry. In the PowerPoint that I uploaded on course sites, really good one, it outlines all the information in the chapter. It's pretty straightforward and very reduced, but it is a kind of a good place to go just to kind of see the same information presented a different way. There's another great picture of a galvanic cell. But more important than that, on one of the slides, there's a link. I highly recommend going there, opening it up on your own. Click on the link. It takes you to an animation. Maybe make a note of it. Take a look at that animation. It shows you this whole process in action. If you just did like a Google search, I'm sure you could find a video showing you the same thing. But the link is really, really good. It's really short. You click on a few things. It shows you zoomed in at the atomic level what's going on during a galvanic cell operating. So something to definitely take a look at. All right, we're going to continue with this and take a look at different kinds of electrodes we can have. All right, there are such a thing known as active electrodes. Whoops. Active electrodes versus inactive electrodes. And this is going to be something you just have to sort of recognize. Active electrodes are the more common types of electrodes. This is when the metals involved, oh boy, when the metals involved in the reaction are used to conduct the electrons. So in the Voltaic cell that we just looked at in the diagram, those would be examples of active electrodes. The electrode meaning the solid zinc and the solid copper. Since they were actually involved in the reaction, they're represented in the reaction, they're called active because they're actively participating in the reaction. Okay, zinc is being turned into zinc ions, and copper ions are being turned into copper solid. So the solid zinc and the solid copper are part of the reaction. They're called active. And like I said, those are more common, I think, anyway. What I do need to get you guys aware of are inactive electrodes. You want to be aware of these. Inactive is when other non-reacting electrodes are used. Students see these, and if they're unaware of them, they get real confused with why are they there, what are they doing, what's happening. They see chemicals that aren't involved in the reaction there, and it confuses them. So that's why I'm pointing this out now. Inactive electrodes occur in a couple different cases, two different cases. We would want to use an inactive electrode if one of the chemicals we're using is a gas. When gases are involved. If you think about it, a gas, right? A gas isn't a metal. So if I'm going to be conducting electrons either towards or away from a gas, I have to put something into the gas. And so I would use some other type of metal to go into it. So that one stands out as being pretty obvious. It's kind of like, hey, I can't have a solid gas in a gas. This is just crazy. It doesn't make any sense. And I'll show you an example of what I mean here. Another place this can occur, if all reacting substances are aqueous. Again, you don't have any solids. In the previous example with the zinc and the copper, we had solids. So it makes sense that I would use one of those solids as my electrode. But here, if I have substances where there are no solids, either I have a gas and or I've got everything in aqueous solution, there's no solids. You can make the argument you could have a liquid as well, but again, that comes up I'd say even in rarer cases. But if you have either of these two substances involved in your cell, then you have to use some sort of a solid to conduct the electrons, a metallic solid. The two most common inactive electrodes that you'll see are graphite. Oh boy, that is not how you spell electrode. Wait, there we go. Common inactive electrodes are graphite. Again, graphite is nothing but solid carbon. Or platinum. Platinum makes a really good electrode, conducts electricity really, really well, and doesn't really react with anything. So you'll see those pop up all the time. And again, I mention these because if you come across a galvanic cell where it has graphite or platinum in it, some students freak out. They're like, is that, are they being reduced? Are they being oxidized? What's happening? And the answer is no. They're not reacting at all. Graphite isn't reacting, and platinum isn't reacting. They're just there to conduct the electrons away from either a gas or, say, an aqueous solution. That's all. There's a really good example of this with a drawn-out cell and everything. You can take a look at it. It's on page 927. It's there on the right-hand side. It's a galvanic cell made up of iodine and then a manganese and permanganate solution. So if you look there, that's a great example of having a gas involved in your anode and the permanganate and manganese as part of your cathode. So there, in that picture, graphite was used as the inactive electrode. Okay, now let's take a quick look at how we represent a galvanic or voltaic cell, how we write them. So this is what we call, oh boy, that is not my pen. Here we go. This is what we call cell notation. So, that's supposed to be an I. There, that looks like a B. There we go. Notation. All right. Yeah, I spelled that right. Okay. Cell notation. So, somewhat simple. To represent a voltaic cell. Jeepers, that's ugly. We use this form of notation. I'm going to use the zinc and copper voltaic cell as an example here. So we would write Zn, and this is our solid. Draw a vertical line. Then Zn2 positive. That's an aqueous solution. 2 vertical lines. Then our copper ions, vertical line, and then copper solid. This would be our cell notation. We have on this side here, I want to use a different color. I haven't used a different color at all yet this entire time. Shame on me. Now I can't remember in the previous video what color I used to write the oxidation when I showed you guys how to balance, but I hope it was blue. This would be our anode. And this over here is our cathode. Now, why would I write that in red? Red cat, red cat, red cat, cathode, reduction, boom, love it. There's no color ox. Anyway, anode is oxidation. Okay. So in our notation, anode is here on the left, cathode's here on the right. The cells, the two half reactions, the cells are split up by a double vertical line. That means you're in a different cell. Now each part of the cell is split up with a single vertical line. Notice we have here our zinc solid separated from our zinc solution. So we make a note of that here. Single line represents phase differences. So we have here our zinc solid, solid in one phase, aqueous in another phase. Those represents our two different parts to our one single anode cell. And over here we have our aqueous copper ions versus our copper solid. Again, different phases in our reduction, our cathode cell. So, very important. Separate each one of those pieces with a single vertical line. Now, this can get a little bit more complicated. I'll show you an example of this right here. Commas separate same phases. Let's see if I can cram this in here. This one's kind of long. I'm going to use the example of the same cell that was on page 927 that I referred to before. The Voltaic cell that had iodine and the permanganate and the manganese. So for this one, we would write graphite. Graphite was the inactive electrode, and I would separate that from our I- aqueous and separate that from our I2 solid. Now this is all the different pieces of our anode. If you look at that picture, you'll see you have a solution of I-. You have I2 solid gathering on the graphite electrode. Boom, boom, boom. Three different parts split up with a single line. And we double line it as we move into the other cell, our cathode. And here we wind up with permanganate, aqueous, comma, H plus, aqueous, comma, manganese ion, and then a line and end it with the graphite. Ooh, well, you get the idea. That's supposed to say graphite. All right. Anyway, that's graphite. That's an E at the end. So the only difference here, guys, is that, hey, aqueous, oops, I forgot the aqueous of the manganese ion. All right. Sorry, cram that in there. Three different aqueous chemicals. They are separated by commas. They're all in the same phase. These are literally all floating around in solution in the beaker. And then a line separates the graphite electrode. So this is a good example of cell notation with an inactive electrode in both cells. Inactive electrode here in the anode and an inactive electrode here in the cathode. Okay. That's how we represent them on paper without drawing a picture. You would want to be able to take an image of a galvanic cell and write a cell notation. You would also want to be able to take cell notation and draw an image of a galvanic or voltaic cell. Go back and forth. Okay, you should be able to take and label all the information that you need from this type of notation. A few things to point out. Notice the salt bridge isn't represented anywhere in here. Again, the salt bridge is not supposed to react with anything. A salt bridge is not doing its job if it's actually reacting. So we don't represent the salt bridge at all. That's pretty much the only thing to point out. I don't know. Cool. All right. Last thing I want to show you guys is how do we tell what's being oxidized and what's being reduced? Okay. There we go. How to determine how to determine the anode and the cathode. That's great. Maybe even already you know that anode is oxidation and cathode is reduction. Well, how do you know what's being oxidized and what's being reduced? So let's figure out how to determine that. To do that, you have to use a standard reduction potential table. Okay, here we go. Standard reduction potential table. This is something you're going to want to have access to and be able to use for lots of questions in electrochemistry. This is actually one of the things you get on the AP exam. So just like your periodic table and your equation sheet, you're going to get this table. I've made copies of the standard reduction potential, laminated I believe. They should be in the on top of the bookshelf with all of our other periodic tables and equation sheets. You guys know where that is. So do me a favor, pause the video really quick if you need to, but have access to that standard reduction potential table. Go get one. If you have the book, there's that table is in the book, and it might even be like a little short table in our textbook. Oh, there is. It's on page 934. That's a really small one, though. There's a bigger one in the back of the book in one of the appendices. Look that one up. Or if you're in front of a computer, go ahead and pull one up on the screen. But have it in front of you and have it every single day as we're learning about electrochemistry. So go ahead and take a second and do that. Alrighty, now that you should have your standard reduction potential table, key word here is the word reduction. Okay, if you'll notice, and I'm going to make a note of this, every reaction on that sheet is a reduction. And that's very, very important to recognize. If I wanted to look up an oxidation, you would look up the reduction and then you could reverse it. Remember, oxidation and reduction are opposites of one another. So every reaction that's reported on that sheet and the value that goes with it, we'll talk more about the value, those all stand for reductions. If I want the oxidation, I can look it up and then reverse it. Look up the reduction and reverse it, and now I have the oxidation. And I bet some of you could maybe even be able to guess what you would do to that value. But we'll get to that here in a little bit. Simple thing to note, the more positive the value, the more likely it is that substance will be reduced. Okay, as you guys are looking at that table, you should notice at the top of that list, the substance that is most reduced is fluorine. Fluorine's the top dog. Okay, fluorine has been at the top of many lists throughout the year, and those lists are the reasons why it gets reduced. Fluorine, we know, is a very, very small atom. Okay, it's the smallest halogen. Has 9 protons in its nucleus. Has an incredibly high electronegativity, pulls electrons away from anything. Again, this is why it gets reduced. Fluorine will tear electrons away from any source it can get its hands on and turn into a very stable ion, F-. So fluorine is the most reduced element. You are, as far as I know, never going to run into a situation where fluorine is oxidized. Now, at the bottom of the list, all the way at the bottom, you have lithium, okay, on this list. Now, this isn't every single element on the table, nor is it every single AP exam reduced. Get it? Reduced. Reduce the number of options on this standard reductions potential table. I think the appendix in our back of our book is bigger. If you look it up online, you'll find bigger ones. But anyway, on our table, which is all we have to worry about, lithium is at the bottom of the list. Fitting, lithium is looking to dump its 1 electron. If you take a look, the likelihood that lithium would gain an electron is incredibly small. Lithium is not going to be reduced. In fact, since lithium is so not likely to be reduced, it's most likely going to be oxidized. Okay? If you combine something like lithium and fluorine, you have a perfect match. Lithium will give up its electron, and fluoride would be happy to take it. So fluorine would be reduced, and lithium would be oxidized. And that's how we use this table. We use it to figure out what's the substance that's going to be reduced and what's the substance that's going to be oxidized. Again, if we use the zinc and the copper as our example here, if all I was told is I'm building a cell with zinc and copper, what's going to be what? Okay, I would need to use that table and look up reductions for my chemicals involved. If you look up the reduction for copper, you should be able to find this reaction. And it should have a standard potential, which is measured in a V, that's volts, by the way. We'll get into more of those details as we do our calculations later on. If you look up coppers, we find that copper has a potential of 0.34, oh boy, that's an ugly 3. 34 volts. Now be careful, because copper does have multiple oxidation states. You'll notice all three coppers are all grouped together. You have copper 1 gaining 1 electron, you have copper 2 gaining 2 electrons, and you have copper 2 gaining 1 electron. Please make sure you look up the correct one. For this example, in the cell that we used before, we have copper 2 plus, gaining 2 electrons to become copper solid. So that has a potential of 0.34. If we looked up zinc's reduction, zinc gaining 2 electrons has a potential, according to our sheet, I'm double checking, yep, a negative 0.76 volts. So this one's pretty clear. The more positive the value, the more likely it is to be reduced. So we see our copper ion gaining 2 electrons has a potential of 0.34 volts. That's what's going to be reduced. And zinc, since the reduction is very unlikely, zinc is going to be oxidized in this case. So when we draw our cell, we would now know that copper, since it's reduced, would be at the cathode. It would be on the right in our drawing. And zinc, since it is oxidized, this reaction would get flipped around. And this would be at our anode, which would be in the left cell. So we'll make a note of that. So copper 2 positive is reduced, cathode, and zinc is oxidized. Done. This is how we could tell, how we know what's being reduced and what's being oxidized. We look at that table and we compare. If we're given a reaction, like we were earlier, we were told the reaction is zinc solid turns into zinc 2 plus and copper 2 plus turns into copper solid. We knew that going in. But in the future, a problem will just say, hey, you're mixing together, say, iron 3 and silver. Draw a cell. What's going to be the anode? What's going to be the cathode? You need to be able to use this table and figure out what's going to be oxidized, what's going to be reduced, and then what my anode and what my cathode are. Okay, that concludes this section. There's some great pictures in the PowerPoint that I've uploaded to course sites and in our textbook. Hopefully you have that. You're going right along with it, and you can look at those close up and get all the detailed information that you need. Next up, we're going to start calculating how we calculate cell potentials and all the implications involved with those ideas. Till then.